Good afternoon, calculus class. So this one is sections 2.6, limit at infinity. So we're going to be doing some kind of a graph interpretations to find out the limit at infinity or different boundary. So the first one, so graph of the function is given and state the following. So as you can see, that's a piecewise functions graph. So limit as x approaches -1 from the right hand side, so for f of x. So approaching from the at -1 from the right hand side, so that means coming from this direction. So that one is what? Negative infinity. And then what we have for the next one, so limit x goes to infinity. So this one looks like it's getting close to what? 1. So there's like a hidden horizontal asymptote here, and that'll be 1. And then limit of f of x as x approaches 2. So for 2, so you might be wondering, there's no exact boundary here, so that's a vertical asymptote. A lot of people might be putting undefined or does not exist, but the thing is that this one you want to use that the limit from the left hand side and the right hand side. And as you can see that the limit approaching from the left here, so is what? Positive infinity. And then same as the limit approaching from the right. So the limit is considered infinity. Okay, so now let's see what else that we have for the rest of this. So this one we're going backward. The conditions are all given. So we need to set up the functions, the graph for the function here. So limit as x approaches 2, so it's negative infinity. So at 2, so you probably see that it's a what? It's a vertical asymptote. So that means, again, this one, what that implies is the limit from both directions. They're always going to negative infinity. So negative infinity, that means they're going to this way. And then x goes to infinity, y goes to infinity. So it's right up here. X goes to negative infinity, y goes to 0. So it could be either right above the x-axis or down below the x-axis. And then x goes to 0 from the right. So the limit, it's infinity. So right up here. And then limit, x goes to 0 from the left. It's negative infinity, so it's all the way down here. And then for those arrows, all you have to do is just connect them. So it's like this. And here's another one. So it's kind of like a reflected cubic curve. And then the rest of this. So it goes all the way to infinity. So again, anytime they want to find a limit at infinity, so basically just finding out the boundary of the functions, the graph of the function. So now, how do you evaluate the limit as x goes to infinity? How do you do that algebraically? So the way that we want to do it, we just want to plug in infinity. So it's 1 over 4 times infinity plus 5. So this one is 1 over infinity plus 5, which is what? 1 over infinity. So that would be considered 0. And then for the other one here, so it's a rational expressions. So basically this one is just like finding the horizontal asymptotes. So as you can see that the leading coefficient top and the bottom. So one is -3, the other one is 5. So eventually it's going to be -3/5. But how do you show the work for this? The way that you want to show the work, you want to take out the end behavior. So what I'm doing here, I want to take out y squared. So we do have 2 over y squared minus 3. Denominator, take out y squared, so you do have 5 plus 4 over y. Again, all those small rational terms, so they're always considered 0 because that x goes to infinity. Well, this one's supposed to be y goes to infinity. So those rational terms, they're always considered going to 0. It's getting smaller and smaller. And then y squared reduced with y squared. So what's left here? It's just what? -3 over 5. And then for that t right here, again, that's another little typo. So this one's supposed to be t. So t goes to negative infinity. So take out the end behavior top and the bottom. So we got 1 plus 2 over t squared. Denominator, so we take out t cubed. So take out t cubed there. So we do have 1 plus 1 over t minus 1 over t squared. T cubed, excuse me. So again, all those small rational terms, they're all considered going to 0. And then once you reduce, this one is considered 1 over t. So finding the limit as t goes to negative infinity. So 1 over negative infinity, which is what? 0. And now, what about for the rational expression with the radical down to the denominator? So the way to do it, so we just want to take out the end behavior again, the one with the highest power. So take out x, so we do have 1 plus 2 over x remain on the top. Denominator, we can take out that square root of x squared. So square root of x squared, then that will be considered absolute value of x. So we want to put that in a minute. So take out this one first. So we do have square root of 9 plus 1 over x squared. Again, those small rational terms, they always consider 0. So now, square root of 9, that would be considered 3, so it's 1 over 3. And now you might be wondering what this is. So this part here can be replaced by absolute value of x. And also the constant term, we can just put in 1/3 right in front of it. It's a coefficient. And once you undo the absolute value, it's considered plus minus x. So it's 1/3 x over plus minus x. Reduce it, so we do have plus minus 1/3. So anytime that you end up with two different values for the limit of one single expression, so that means this one is saying that the limit does not exist. Okay, so now let's see what else. And then the rest of this with the radicals, so this one is getting a little bit more complicated. So now take a look at that for e. So this one, what we can do, we can put that 1 underneath that rational, the linear and the radical form. And what we can do here, we can multiply the conjugate of this top and the bottom. So we can multiply that by x minus square root of x squared plus 2x. So what we're trying to do here, we try to rationalize the numerator. So what we found, so we do have x squared minus the quantity of x squared plus 2x. And then the denominator, we just want to keep that conjugate. So once you cancel it out, so we got x squared minus x squared cancel, so we got 2x over. Now got to be careful with this. The denominator, we can take out x, and also we can take out that the x squared, term, so that would become plus minus x. Okay, but the thing is that for this one, x is actually going to negative infinity, so that means it's considered the negative x. So what we found here is supposed to be x plus x down the bottom. So once you take out that x here, and then we do have square root of 1 plus 2 over x. So this one's getting smaller, so this one eventually is going to be what? 0. And then what we found here is supposed to be what? 2x over 2x. Okay, so 2x over 2x. So eventually it's going to be 1 for the limit. Alright, so now what about for this one? This one, A and B and C. So those are the arbitrary constant, and they'll consider any real number. Again, so the same kind of technique. So multiply that by the conjugate, top and the bottom. So this one, let me just do it on the other page here. So we do have limit as x goes to negative infinity. So square root of x squared plus bx minus square root of x squared minus cx over 1. Okay, making sure that this one plus cx, excuse me. So conjugate, top and the bottom. So this one, we multiply this one by square root of x squared plus bx plus square root of x squared plus cx. Denominator, same element, conjugate. So now what we found here, we got x squared plus bx minus the quantity of x squared plus cx. And it's all over the conjugate, square root of x squared plus bx plus x squared, square root of x squared plus cx. So x squared minus x squared, that's 0. So what we left here, so we got bx minus cx. Denominator, we can always take out the oh shoot.